Yes, perfect.
That's fine. All right. So today Vlad will present his latest publication that he did in the lab. So it will be more technically oriented toward that kind of scientific contribution. I know Vlad since 2013. I had to check it out. He was doing a internship as a master's student when I was in Zurich, and we worked together since there. We even tested robots for Italian firefighters together. And Vlad was part of two EU projects on search and rescue. So that is typically his skill set. He's working in the lab since 2 years. Is the initiator of our international participation to the DARPA Subterranean Challenge, and is also the scientific lead on our research program for SNOW. That research program is where we test and investigate and develop autonomous navigation in winter conditions. So within that context, I will let him talk about his latest paper, and it's up to you, Vlad.
Okay, thanks for the introduction. I will share my screen, my presentation. So I practiced yesterday. Screen, yes, share. And let's go to full screen. I need to turn on my laser pointer. Is it all right? Okay. So thank you for attending this presentation. We've been working on an interesting topic of applying and using global satellite navigation in difficult environments together with our master students, Philip and Philip. And I will show you what we have come up to until now. As Francois said, I'm a postdoc in his office, in his laboratory, Norma. And generally what we do is that we take mobile robots, we throw them into difficult environments, into snow, into forests, and we wait and see what breaks. And when something breaks, either hardware or software, we try to figure out why it broke. And while doing that, we usually learn something new. And it sometimes leads to interesting papers. Like in this case, when we tried to see if we can predict whether any of your preferred global navigation systems, such as GPS or Galileo or GLONASS, something else, will actually work in an environment that you choose for your robots. It might be autonomous car, it might be autonomous robot somewhere in the forest, or maybe a boat. So I guess you know that, and now this is GNSS, it's Global Navigation Satellite System. I will call it GPS from now on because it's more easy, but you can imagine any other system. So I guess you know that your GPS will be working fine somewhere in some open area, like like a desert, or maybe sea, and perhaps a very large parking lot in front of Walmart. But in a city or in a forest under trees, you know it's not so good. And that's because the signals that come from satellites don't always go directly into your GPS receiver. They sometimes get blocked by obstacles like buildings, rocks, and they also might go through vegetation. There are also some other effects, but in our work, we focus on these two main problems. Now, how it looks really in practice when we really try to use GPS. This is an experiment that we did. Let's say you want to take the robot like this and pass through some open area, then through a forest, and you just record the position as reported by your GPS receiver. This is the result, what you get from one GPS receiver. You can see that the trajectory is quite fuzzy, and this is definitely not what we were driving in this experiment. We were navigating the robot in straight lines, but here close to the building, and here around the library, and also in the forest, the localization error is quite hard. 5 or 6 meters localization error is not an exception. It's maybe a rule. So if you just want to record the position and put it into a map, that's fine. You just end up with something like this, and you get annoyed, and you have to repeat it maybe later with some other solution. The problem comes when you try to use it to navigate your robot or control it autonomously. Of course, if such data go into a robot controller, you end up with the robot hitting the wall or a tree, or maybe it will fall into a lake. So in that case, you can try to get it better. One approach to this is to use additional source of corrections. It works like that you use a static, another GPS receiver, which is stationary somewhere and just listening to the satellite signals. And the fact that it's not moving helps you to correct your own localization. The limitation here is that you need to be able to transmit in real time the information from the static antenna to your mobile robot. And this link is somehow the weakest thing in your navigation. If this link breaks, for example, if you're too far from your reference antenna, then you revert back to that ugly GPS that you saw before. Now, we are not the only ones who look at this problematic. In the state of the art, there are 2 big groups of papers. One of them uses 3D representation of environment. It's usually urban environment, and the models, they come from Google Earth maps, or maybe OpenStreetMaps. And these approaches, they can tell you which satellites from the sky might get blocked by the buildings. And even some of these satellites, the signals from them can come to you by bouncing off some buildings, and these approaches can tell you that this satellite you are not supposed to receive signal from, but you are receiving it, so it means it bounced, and they correct the localization knowing that. The other big group of publications is focused on forests, and they look on the composition of trees, vegetation, the density of the vegetation, and based on that they try to predict if your GPS is going to be good at that part of forest or not. So what we do, we try to combine these 2 worlds into one solution, which tries to predict how many satellites you are going to be able to use based on a map and some representation of the environment. In our case, because this is our specialty in the lab, based on 3D point clouds, they are captured by laser range finders, and on a known constellation of satellites. This is fortunately for free. All the systems transmit this information to you, and you can also download constellations, like future constellations, for a few days with high precision from the internet. And finally, we try to combine these things and try to estimate is it going to be good or bad to use GPS at that given spot, at that given date in your environment. And the motivation, as I've suggested, might be that you want to be able to plan trajectories. And this work did something similar for planning robot trajectories such that it never gets too far from an access point. They don't want to lose the contact with the network, so they plan to go through them. In our case, it would be similar. We just want to plan trajectories which don't go through portions of the environment which has bad GPS reception, because we know that we get into trouble there. So now, how we do it? We start with the point cloud with a 3D representation of the environment. And this is an example. On the left, you see one building in our university campus. This is taken from Google Earth, just to visualize what you're looking at. On the right side, this is a 3D point cloud taken by a robot which followed the red line. So we get a map like this. Just to explain, what you see here is this portion here. Those are the windows and walls in the yard of that building. This black planary structures, that's the ceiling of the ground floor. The robot could go under, so all these are the ceilings that the robot saw from beneath. Once more, to give you an idea of the 3D shape. Okay, so now we have a point cloud, and since in our approach we want to distinguish between vegetation, that would be the forest case, and between solid obstacles, that's more like the city case, we need to be able to tell which portions of the point cloud are rather vegetation, which are solid obstacles. Our approach is to look on local geometry in the point cloud to see if the local shapes are more like planes, planary surfaces, which for us indicate solid structures, because man-made structures are usually flat. And this also holds for rocks and things like that. On the other hand, vegetation usually looks like a uniform distribution of points in space when taken by a laser rangefinder. It's because of the leaves and small branches. You will get a bunch of points which are distributed uniformly. And now, how we actually do this? We go through the whole point cloud, and for every point, we take its close neighbors, let's say 20 closest points, and we look on the shape these points form together. If it's more towards, okay, how to tell what shape it is by taking covariance matrix of the distribution of these points, and the eigen numbers of this covariance matrix indicate the shape. We define two functions, spherical function u and planar function s. These two functions just consist of comparing the sizes of the eigenvalues, and they have the property that when the shape of the points goes towards spherical uniform distribution, the function u gets closer to 1. If it's more like plane, the function s goes towards 1. We combine these two functions just by subtracting them to get this classifying function which for points which are close to planary surfaces or resemble planes, the function goes towards -1, and then the same function goes towards +1 if it's more like spherical uniform distribution. In this point cloud, the red points are those points classified as planes. You can see that all these red points on the ground and on the ceilings, on the building, and on the walls, those all would be classified as planes. On the other side of the spectrum, the points here on the trees, they are all classified as vegetation or uniform distribution points, but we understand it as vegetation. And the function actually goes smoothly from -1 to 1. So all in between, and that's usually branches on the walls or these columns and maybe lamp posts, they lie somewhere around 0. So this way, we are able to tell whether the points belong to trees or solid objects. Now, what to do with that? In the next slides, I will be showing 2 examples. A spot in the map taken close to trees, and then another one taken close to a building. And there will be such a sequence of views that you see here on the overview. This is a pipeline, how we start with point cloud and a known constellation, and we end up with the result, which is the sky view with expected satellite coverage. So first block, the first image is just a view from camera. Next to it, you have a similar view, but with a point cloud. So these trees, they come up like points, and in our plots, if it's green, it's the vegetation, and if it's brown, it's more towards the solid objects. And we take a sky view, put the points that we see from that point, from the ground. To be able to compute something, we need to discretize the sky view into some finite bins. And for each bin in this sky view, we know what type of points there are and how many. Further, to be able to find the areas of the sky view which are not blocked at all, we do this simple mask. And the idea is that if there are no points, or it's just like 1, 2, some noise, we know that in these portions of the sky, there will be no blocking of the signal at all. We then combine these two masks, the mask which tells us what points there are and what areas are not blocked at all, and we create an attenuation mask. This tells us the areas that we expect high attenuation of the signals or complete blocking. What we do next is that we download from internet or just wait for the satellite to send it the given constellation of satellites as if there were no obstacles in the sky. We combine these two masks and then we get the result. So once more with bigger images, and these are the two examples. The top part, there's the vegetation. We are standing next to some trees. The bottom part is we are standing in the inner yard of one of the buildings in the campus, looking upwards. So as you would expect, looking on the point cloud from the same spot, up here we see a lot of vegetation. Down here we see all those points labeled as solid obstacles. This is the discretization step when we split the view into discrete bins. These portions of the sky are the unobstructed ones. We know that the signal will go through them easily. Combined with the point cloud data, we get the attenuation masks. You can see that up here with just the vegetation, attenuation is not so bad. The more dark, the more violet, the more attenuated the signal would get. It's much worse here because all of those points indicate solid structures, so you know you shouldn't pass any radio signals through that. Next one are two satellite constellations which were there at the moment we were taking the data. And when we apply the mask from the previous step, we get the result. So here you can see we see most of the satellites still just slightly attenuated, but in the bottom part, when we are standing under the ceiling, you can see that just the satellites that were on the portion of the view when there were no buildings, they get through, and the rest down here slightly, but there used to be much more satellites, many. Okay. In this next part of the talk, I will show you how we got to the model and how we verified that the result that we get actually makes sense. We made two data collection platforms. The first one was just a box with the two sensors that we need for our purpose, with the laser rangefinder and a GPS antenna. And this platform was nice. It was light and could be dragged behind a snowmobile and mounted on a small robot, and we collected some experiments with that in the campus and in the Forêt Montmorency. And 1 year later, we could use our new robot to carry the sensors around for us. This actually has 2 antennas, but we were using just 1 antenna and 1 laser rangefinder, as with the previous data collecting option. The places when we collected experiments were several areas here in the campus. We were interested in the close proximity of buildings. We were interested in the open areas and the vegetation. And in the Foreign Morenci, the interest was in the pine forests, which are very dense, and it was interesting to see how much signal they actually attenuate, and they actually do quite a lot. And during the experiments, as usual, we learned new interesting things. One is that there is a lot of curious animals in the forest, and especially these birds, which tend to land and sit on your GPS antennas. You can imagine when you need to collect your reference data for the paper, there is a bird sitting on the antenna. It's not so good. So during the experiments, actually I had to stand there as a scarecrow, making sure that there are no birds on the equipment. Another thing that we found out was that even if you have several GPS antennas and you have that better RTK corrected localization, in the case that your moving antenna is in an area when there are like 2 or maybe 4 satellites available, the RTK will not save you. Even this better solution will not provide any reasonable data, which is sometimes forgotten or not taken into consideration in the state-of-the-art papers. Sometimes you can read that you will use an RTK GPS, and it's a good localization. But we have found out by the difficult way that this is not always the case. And how we get now what the results are, how well does it work? I have 2 examples here. The first example is a short trajectory that we took with one of our robots. We start here in the parking lot. We pass under the building through the passage, turn around in the yard, and go outside. And we compare our result, which is the black line, number of satellites that we expect to see, with the actual number of satellites recorded by the GPS antenna at a given moment. It's slightly noisy, so we show you an average value with the variance. And we compare ourselves to a simpler model, which takes into account just occlusion. We call it a binary mask only, and this is approach where you would actually just look on your point cloud, and any instance that there would be something between you and your satellite, you would just scratch the satellite from your final sum. Here, close to the building, these 2 approaches give you quite similar results, and this is because really most of the obstacles are man-made hard structures, so they don't let signals through. You can see it here when we pass under the building, back and forth. You'll be see dims in the expected number of slides. Where we do see the difference is when we start going into the vegetation. In this experiment, the first portion is just driving on the open area, maybe around the buildings. It's this portion of the plot. But the difference comes when we enter the forest and we do this loop around. You can see that if you were just simply masking out satellites based on the obstacles that you see around, you would get much more pessimistic estimate compared to the real situation. In our approach, we know that in the point cloud, all those obstacles are actually vegetation, and therefore we adjust the value, so we get more accurate expectation of the signal. Moreover, we can reuse the model not to look at the satellites, but to look at the expected signal coverage from your static RTK reference antenna. Here we compare to a simple model which takes into account just the distance, because as you get further and further from the antenna, the signal drops. But again, when we get into the vegetation and there are obstacles or the trees between you and your reference antenna, in this portion you can see that we can get closer estimate of the signal received compared just to one that takes into account just the distance. This part we were going closer and further from the antenna, but here that's the first. And finally, when we can when we can project the expected number of satellites, we can do this for every point in the map for a given constellation as we wish. So this shows you that you can move around with the satellites in the sky. Usually, this is an example. Usually, you would just download the constellation for your given day or the time, and you would see which portions have a good reception and which portions are not a good idea to go to. This is slightly larger scale. You can see that when satellites are somewhere on the north part of the sky view, you will get a bad reception behind the building expected. And we can do the same thing for your static reference RTK antenna. You can position it somewhere in the 3D point cloud map and compute what is the expected radio signal strength in any part of the map. Here we see that behind the buildings you get no reception at all, and maybe you want to reposition your antenna to get a better reception here compared to the case before. So I'm approaching the end. Just to recap, in our approach, we predict the number of satellites we expect to be able to use at the given position at the given map, and we base this on a 3D point cloud map and given satellite constellation that you can download from the internet or just wait for the satellites to tell you. And in our approach, we consider both occlusion by big buildings and obstacles and the absorption effects caused by the environment. And the usage is, as I said, usage for planning trajectories of robots, trying to get them or navigate through parts of your environment which have good GPS coverage, or maybe to be able to, when your localization deteriorates, to be able to go to a place when the reception is better and improve your localization. So that's all from my side. Thanks for the attention. And I guess I will ask Francois or maybe Annette to read the chat if there is something.
All right. Thank you very much, Vlad, for your presentation. Is there any questions from the audience? You can use your microphone or the chat if you want. We'll wait a bit in case someone wants to show up. I might start with the icebreaker question. Why did you throw a robot into a lake?
That's a very good question. It wasn't because of GPS. I guess you understand that this wasn't related to GPS. It was to see if it's really as waterproof as the manufacturer says, and also to see what is the buoyancy and to see what is our budget for putting stuff on the robot if we take it into the or we pass it. Also to have fun. Come on. So yes.
All right. Is there any other questions? I see that there's a couple of profs in the audience.
Hi, I want to ask a question to Vlad.
Yes.
It seems that when you did your experiment, it was a sunny weather, but do you think you will have the same result like during a snowstorm, for example? Do you think your result should be accurate enough?
It's a really good, that's a good point. I think this might be a weakness of what we do. I think clouds, not so much, but really heavy snowstorm might make it much worse because a lot of water, you know that the signals that the GPS and the other systems use are around 1 point something gigahertz, which gets absorbed by water. And you have water flying around you, I guess the signal will be much worse. But you know, if those things are not in your map, in your 3D map,
yeah,
it's like the bird. Like you cannot expect the bird. I think it would have to be more reactive, that you would actually detect something's changed around you, so you might update the map. On the other hand, actually, I think it might work quite well because the snow will be flying around you, so the same distribution as the leaves in the vegetation. Of course, the density might be slightly different, but yeah, might be done in a slightly more reactive way based on what you see.
Okay, thank you.
All right, so we have a question from the chat. Dominic is asking, could you use your solution to switch between localization solution if, for example, you would be driving in an open road and then suddenly going off-road in the wood to switch to a more computationally expensive solution like ICP or moving on point cloud? So could it be something that is reactive and computed real time?
Definitely. The computation is not that crazy. You can quickly get the geometry from the point cloud because usually our maps contain the knowledge that you need. So you just extract the eigenvalues and get the geometry. What's slightly more taking time is selecting a point in the map and going through all the points which are relevant to you and assembling them to the sky view. But yeah, if you're not driving super fast, and usually you have some time, and this value is valid for some space around you, it shouldn't be a problem. So this could be done in real time. On the other hand, you are already there, so you already have your GPS antenna listening to the satellites. So you know what you are hearing, so you know how bad you expect it to be. But this is more for planning. So the question is, should I go into the forest from the open road, and should I start preparing myself for building a map? Yeah, in that case, yes, that you might want to fire up some other systems sooner before you actually get into the bad situation that you don't get the GPS.
All right. So the idea here is that it's more used for predicting the coverage more than live reading. We have a question from Amar also.
Okay, hello.
Hello.
I have a question about the navigation here. Is it done online, or do you first scan the environment, then try to navigate on it?
Again, it's this approach is more for prediction. So in our experiments, we first made a map by moving the robot around, and we did the prediction based on that. but the same thing could be done while you're there. And again, that's the question: if you already have a map, so you can do the planning and the computation beforehand. But if you're moving through the environment and building the map, this is as close as you can get these values. But usually, sometimes you go through an area, you get the map by looking at it, and then you can reuse it during your online the later
Yes.
parts of your mission.
Okay, so I was just wondering, because when you take scan from the ground to the sky, the trees can, like with time or season change, they can lose the leaves, and that may change the 3D scanning. So
That's
do
completely
you,
true. That's a really good point. We see it here in the campus that the character of the point cloud changes when the leaves are down. It's more branches. So compared to the leaves when you have more like the vegetation geometry in the point cloud, and it actually changes the values. So that's going nicely with the big problem in robotics, which is the long-term autonomy and long-term operation of robots in some environment.
yes,
And then depends, do you have multiple maps? And I guess everything can be improved, even this. So
yes,
you see that we do local estimation of the geometry based on the point cloud, but there are now ways to use machine learning to recognize what's what. So you don't recognize anymore like just 10 points and say that's vegetation. You could actually recognize that bunch of your map is a forest, and then you probably know how the tree behaves through the year, so you can extrapolate on that. They
yes.
haven't tried that, and this is like an early stages. People are
Okay. Well, I work on place recognition. We have the same problem, and I was wondering whether you can also add a camera looking like to the sky, and you can train your network to recognize already visited place, or well, in this case, could be just the trees, and yeah, you can do like a cross-seasonal recognition without like scanning the 3D, the forest in 3D.
Yeah, I guess you could. Depends on how well this would work in a forest, because it kind of changes through the year that we know.
Yeah.
Just with camera, there is this issue that you have to be able to, at least not for localizing. For localizing, you don't need to figure out if it's dense or solid object. But for our purpose, then we need to tell what happens to the radio signals coming from the satellites. We would need to be able to classify those portions of your sky view in that camera view, and then do some thinking about is it a building, so I don't expect the signals to get through, or is it just a piece of tree canopy, and then you can use it
Okay.
to pass part. The thing that we get here with the 3D maps is that we see behind. Well, we see behind the things if we've been there behind the things, but the more complete 3D map, for example, with the radio, the reference antenna, it helps us to know what is the structure of the environment, because we know that the signal needs to go through 30, 40 meters of the forest. With the just camera image.
Well, I was talking about combining both of them, not only the camera.
One of the point here is making the difference between the global representation versus the local representation. If we only use the camera, essentially point cloud are a bit easier to extrapolate or interpolate to the whole ground plane as the image up there. For the camera is always a lot viewpoint dependent, but you gain the advantage of all the machine learning toolkits that can go behind. And for the other higher level questions, for multiple seasons. That one is harder, even for camera. So we did early experiment by driving and measuring the noise in summer under the tree canopy and in winter. And clearly the GPS noise is changing with seasons. Now the question is whether, so in that work, we deal with, you have a current representation of the environment, trying to project what it would look like in summer. That one is a bit harder from at least from the geometry perspective.
Okay.
Yeah, you are
But
adding semantics. So
I know that there's some very cool machine learning work that take an image in summer and are able to modify it to make it look like in winter, and vice versa. I saw some of those going out. It's typically more for the visual appeal. Now, whether we can extract the geometry out of that still open topics. But there's some, when Vlad was talking about multi-season localization and multi-season autonomy for a robot, that's let's say the latest trend in robotics right now. Those are big challenges.
Okay, thank you.
Is there any other question? How are we doing with time? So, okay, we can still take one or two questions if there is any.
I will stop sharing the screen so we can see each other.
So otherwise, thank you very much for your presentation.
And thanks for attending.
And I will let Annette conclude because I have no idea. I guess you can announce the next seminar.
Yeah, the next seminar will be Dominique, who will be presenting. I don't have the title in front of me, but it'll be next Friday, and I will begin to announce it as of Monday.
It will be something related to a robot and control.
So you're welcome to come back next Friday for another seminar from NORLab. Thank you very much, Vladimir.
You're welcome.
Thank you. Bye-bye,
Bye,
everybody.
Bye-bye.
Thanks. Bye-bye.